So welcome back. The way I solved this, or as far as I can get, is I start the place I always do for trying to calculate work, which is that it's always equal to the force that we're pushing against. We'll assume reversibility. So we can make the equivalency between the external pressure and the pressure of our system. But in this case, we don't know what the function of pressure, we don't know the shape of the function or the form of the function of pressure as a function of volume. So if we were to go to integrate this equation, we're stuck. We can't solve this integral. So we're just going to leave this here in limbo for a bit and move on to another part of the problem that we can solve. So activity 2 for you is to find an expression. For du. That's again. I wonder if the speakers are good enough that you can hear dogs in the background. All right. How'd that go? Coming back. Maybe I'll use a new page. So to solve for du, I'm going to use the same trick that I used for a constant pressure process. Meaning I'm going to exploit the idea that u is a state function. And so I can choose any path I want to calculate. So let's draw my adiabatic process from some cold temperature to some hot temperature because we're compressing. State 1 to state 2 prime. And you can pick any path. I'm going to pick constant volume heating and then isothermal compression for my path. And I'll call the intermediate state state A. So for state 1 to A, du is going to be equal to CV dt. For state A to 2 prime, du is going to be equal to 0 because it's isothermal. And so for the total process, for state 1 to state 2 prime, du is going to be equal to CV dt plus 0, or just CV dt. All right, so activity 3. Use the fact that delta Q is equal to 0. We have an expression for delta W, which is minus P dV. And we have an expression for du, which is CV dt. So use these 3 equations to find an expression for the final temperature. And the final temperature is going to be a function of your initial temperature, your initial volume, your final volume, and the constant volume heat capacity. So pause the video and see if you can derive this expression. All right, welcome back. So I'll start with the equation for the first law. But dq is 0 by definition of the process. In the earlier two exercises, I derived equations for both du and delta W. So I'm going to write them here. I'm going to assume an ideal gas, so that means I can put in a function that I know for pressure. So I end up with CV dt equals negative R T over V dV. And then what I'm going to do is I'm going to solve the equation. I'm going to put temperature on the side with the temperature differential, and I'm going to keep volume on the side with the volume differential. So I end up with CV dt over T equals negative R over V dV. I'm going to integrate the expression. And I'm going to note that in creating the expression I just did, there's an assumption I made. So make sure you understand what the assumption I just made is. If I solve this integral, I get CV over R, natural log of T final over T initial, equal to the natural log of V initial over V final. Notice that I incorporated the negative sign from the integral by switching the order of this natural log, which you can do just by the property of natural logs. By another property of the natural logs, I can rewrite this with the CV over R term in the exponent. Since both sides are now in terms of natural logs, you can basically raise both sides of the function to 1 over e, and the natural logs cancel, so you end up with T final over T initial raised to the CV over R equals V initial over V final. And then, but the thing we asked for, the thing we wanted, was an expression in terms of T final. So what I'm going to do is I'm going to raise both sides to R over CV and bring T initial over to this other side to get the final expression. T final equals T initial. Times the ratio of the initial and final volume raised to the gas constant divided by the constant volume heat capacity. That was our mission. So now, this function is the function that we can use to describe the shape of this curve. This is calculating the final temperature, which is the thing we often know, but you could again use the ideal gas law to replace, you put temperature in terms of, you could use the ideal gas law to replace temperature with pressure, so you get this, and you would have a similar equation in terms of pressure. You can do the same thing with temperature. So we actually have 3 equations relating initial temperatures, initial and final temperatures, initial and final volumes, and initial and final pressures for adiabatic processes. Okay, thanks. I hope those instructions were clear, and I'll look forward to your question class.